So in our previous example problem for day 17, we worked with a 2D elastic collision. And I said that I'm going to give you one of the two results so that you then solve it and then prove it's elastic afterwards. That is because it's just way too mathy for a non-calculus-based class. What I will give you and have you solve it completely knowing that it's perfectly elastic is I will give you one-dimensional where we're working in a line problem. So this is an example of one of those one-dimensional problems where we've got a piece that is acting in a straight line. So in this case, I have a track star who is running at a velocity of, it'd be great if I wrote down these numbers, 7 meters per second. So velocity track star, 7 meters per second, and has a mass of 65 kilograms. And they are running full speed at a sumo wrestler. Sorry, sumo wrestler. That sumo wrestler is running or moving towards them, probably more of a jog than a run at this point, but they are going, velocity of the sumo wrestler is 2 meters per second. And they have a mass of significantly more than the track star of 230 kilograms. So what's going to happen is at some point they are going to hit, and the result of that hit should be in some way, shape, or form them being thrown backwards. With some velocity. So we have a perfectly elastic collision. And I'm telling you this guy is perfectly elastic. We have solved for the condition, we've solved problems where we talk about maybe the sumo wrestler hugs the guy and tackles him, and there's a perfectly inelastic where there's conservation of momentum, but we don't have any conservation of energy. In this case, they just bounce off of each other. There's no energy lost between them. So for this, what we're going to have is we're going to have a couple of equations. We're going to start with, we have our conservation of momentum. So our conservation of momentum is going to tell us, so sum of momentum in, I'm going to write momentum as mv, and we'll call this 1, we'll call this 2, and we will call this positive. So sum of momentum at 1 is going to be equal to the sum of my momentum at 2. And just like we were doing with our last equation, we're going to go ahead and break this out into our components. We have the mass of our track runner times the velocity of our track runner at time 1, plus the mass of our sumo wrestler times the velocity of our sumo wrestler at time 1 is going to be equal to the mass of our track runner times the velocity of our track runner at time 2, plus the mass of our sumo wrestler times the velocity of our sumo wrestler at time 2. And if I started plugging things in here, I have mass of my track star, I've got velocity of my track star initially, I've got mass of my sumo wrestler, I've got velocity of sumo wrestler initially, mass of our track star. I don't have my velocity of my track star at time 2. In fact, if I were remembering to do this, my what to finds, that is, I don't know what friend finds. We're finding it, not our friends. What to find is going to be, we want our velocity of our track star at time 2, and we want our velocity of our sumo wrestler at time 2. So that's what we want, and that's what we want. We do have that. So we've got one equation and two unknowns, which means we're going to need another equation. And that other equation we're going to use the conservation of energy equation. But this is going to be a conservation of energy for only 1D elastic collisions. I'm not writing everything out there, especially with the blue marker dying. So with that, we have a special equation that we can use for this that was introduced in class. So this equation is basically a derived equation where we took our whole kinetic energies in equals kinetic energies out equation and we combined it with our momentum and we came up with a much simpler piece to solve. So this shortcut equation is going to be the velocity of the first object. We can choose either object. So in this case, I'm going to choose my track star at time 1 plus my velocity of my track star at time 2 is going to be equal to the velocity of my sumo wrestler at time 1 plus my velocity of my sumo wrestler at time 2. And that is, again, it's just a combination of the previous equations solved for what we're after right here. And there we go. What we're going to do here is we're going to take these two pieces. So I, again, have a velocity track star at time 2 and velocity sumo wrestler at time 2. And I am going to go ahead and I'm going to combine these equations, two unknowns, in order to solve for it. So I like to do this with letters, and I think with the amount of values here, this is going to be a lot easier. So what I am going to do is I am going to solve, which did I solve for? I solved for the velocity of the sumo wrestler at time 2. So I said the velocity of the sumo wrestler at time 2 is going to be equal to the velocity of the track star at time 1 plus the velocity of the track star at time 2 minus the velocity of the sumo wrestler at time 1. And then what I'm going to do is I'm going to take this value right here and I'm going to plug it in to this equation. So then at that point, this is true, this is true. When I plug in for here, I have everything in terms of one value that I'm trying to solve for. So in this case, my overall equation becomes really messy. Mass of the track star times velocity of the track star at time 1 plus mass of the sumo wrestler times velocity of the sumo wrestler at time 1 is going to be equal to mass of the track star times velocity of the track star at time 2 plus mass of the sumo wrestler times velocity of the track star at time 1 plus velocity of the track star at time 2 minus velocity of the sumo wrestler at time 1. And at this point, the only values I don't know is I don't know this value and I don't know this value, which is the same value. One equation, one unknown, we can solve it. And to prove we can solve it, you could have started plugging letters in. I just didn't want to write all numbers in. I didn't want to write them all out. In fact, I didn't write them all out in my work here. I just kept with letters, but to switch it in, mass of my track star is 65 kilograms. Velocity of my track star initially is, well, I said to the right was positive, so I've got 7 meters per second, and that's a positive. Mass of my sumo wrestler was 230 kilograms. Velocity of my sumo wrestler is, I wrote it down as 2, it is negative, because after I wrote it down, I defined positives to the right, so that's negative 2 meters per second. That is going to be equal to the mass of my track star, which is 65 kilograms again, times the velocity of my track star at time 2, which is what I'm trying to solve for, plus I'm not going to have enough space to write that out, so I'm going to put this whole line below here. Mass of my sumo wrestler, which is 230 kilograms, times velocity of my track star at time 1, which was positive 7 meters per second, plus the velocity of my track star at time 2, minus the velocity of my track star at time, my velocity of my sumo wrestler at time 1, which was negative 2, so minus the negative 2 meters per second. That'll be the equivalent of adding 2. So there. What I can do is I can do all the math. Let's do it. 65 times 7. So I've got 455 kilogram meter per second plus 230 times negative 2. So that's actually going to be a minus 460 kilogram meter per second is going to be equal to 65 times VT2 plus, I'm going to do this 230 times VT2 plus this 7 minus a negative 2 is 9, so 9 times 230. That is 2070 kilogram meter per second, and these are both kilograms, just to keep track of units there. So what I should be doing there is I've got 455 minus 460, that's going to be negative 5, minus 2070 is going to be negative 2070 kilogram meter per second. I'm going to divide that by 65 plus 230. So that I have just VT2 on the side. So VT2 is going to be equal to negative 270 divided by 295. So negative 2070 divided by 295. I get a value of negative 7.017, which is the same value that I have on my notes, meters per second. So after the track star hits it, he bounces back and he's going faster than he was going forwards. He's going backwards now, 7.017 meters per second. Okay. Now, to finish off the problem, let's go back and let's talk about the sumo wrestler. So now that I have this number, blue wasn't working great, pink isn't, and green is not terribly different. So let's hopefully get pink going a little bit. So pink, we have this, which means that I can plug back into here or I can plug back into here. For me, this looks a lot easier. So we have VS2, which is what we're solving for, is going to be equal to velocity of the track star at 1 was 7 meters per second. Velocity of the track star at 2 was negative 7.017 meters per second. And velocity of the sumo 1 was negative 2 meters per second. I add all of those up. I get that the sumo wrestler, velocity sumo wrestler at 2 is now positive 1.983 meters per second. So he is also going backwards. And at this point, they are going at exactly, they have run into each other, and we could have solved this in different ways. We could have changed these two and made them work for different areas that are conservation of momentum, but the only speeds that they bounce off, and it is perfectly elastic, are when these are true. So we have to use both of these equations in order to solve for it. So that is elastic collisions. And I think that might be the last for exam 2. I'll have to double check, but take care.